Okay, lecture problems for Chapter 17. Take a second to read the problem. I'm given a penny that has an initial length of 1.9 centimeters, and this is at some initial temperature, which I'm told is 20 degrees Celsius. Copper pennies are not actually made out of copper. It's too expensive. They're made out of a metal alloy. We're told now that this metal alloy has a coefficient of linear expansion of 2.6 times 10 to the negative fifth per Kelvin, and we're asked for the diameter at Death Valley, a different temperature, very hot, I've been there, as well as in Greenland, very cold. So for part A, let's take a look at Death Valley. My change in length is going to be equal to my initial length multiplied by my coefficient of linear expansion multiplied by the change in temperature. So it's going to be my initial length. So that's going to be my length minus my initial length is equal to all that stuff right there. So I can simply say that my length is going to be equal to my initial length plus my initial length multiplied by the coefficient of linear expansion multiplied by the change in temperature. So this is what I'm going to use for both parts A and part B. In part A, I know that the temperature is going to change. It's going to go up. So my change in temperature is going to be 28 degrees Celsius. That's also going to be equal to a change of 28 Kelvin, because I simply add 273 to both of those, so the change in temperature is going to be the same. And so I say for Death Valley, my length is going to be equal to my initial length, 1.9 centimeters. Just going to leave it in centimeters for this one, so my answer will come out in centimeters. My initial length is 1.9 centimeters. My coefficient of linear expansion is going to be 2.6 times 10 to the negative fifth per Kelvin. And my change in temperature is going to be 28 Kelvin. The Kelvin and inverse Kelvin will cancel each other out. And kind of as I would expect, my diameter would go up, and it's going to go up to be 1.9.014 centimeters. So that's my diameter of my penny in Death Valley. For part B, it's going to be exactly the same, except for the change in temperature is going to be equal to negative 73 degrees Celsius, which is going to be negative 73 Kelvin. And I go about this the same way. My length is going to be equal to 1.9 plus 1.9 multiplied by the same 2.6 times 10 to the negative fifth per Kelvin. And now I have my negative 73 Kelvin, so my length is going to decrease. And the diameter of my penny in Greenland is going to be 1.8964, and it's still in centimeters. Okay, take a second to read the problem. Here I have some ice with a certain mass, 0.2 kilograms, and initially the ice is at a temperature of negative 40 degrees Celsius. That's added to some water of an unknown mass. The initial temperature of the water, temperature 1 of the water, was initially 80 degrees Celsius. And then at the end of the day, the ice is going to melt, and it's going to have a final temperature that's going to be also equal to the final temperature of the water. It's going to be 20 degrees Celsius. Now I'm looking to find the mass. I know no heat is lost to the surroundings, so that says that the energy of the ice plus the energy of the water must add up to be 0, so energy must be conserved. So the heat that's lost by the water is essentially going to be gained by the ice. So I can say that the heat of the water is going to be just like that. So let's calculate what these guys are. We'll do the water first, since it's the easiest. The heat change for the water is simply going to be the mass times the specific heat of water, it's going to be the mass of the water, times the change in temperature of the water. I know that the water has an initial mass. I don't know what that is. I want to solve for that. The specific heat of water is going to be 4190. So specific heat of water, 4190. And that has units of joules per kilogram degree Celsius. And then the change in temperature of the water is going to end up at 20 degrees Celsius, and it started out at 80 degrees Celsius. So I'm going to end up with my heat of the water. It's going to be negative, as I expect it to be, 251,400 joules per kilogram, and that's going to be multiplied by the unknown mass of the water. Now the ice is just a little bit more complicated, but essentially what I need to do is it's going to take some energy to take that ice and raise it up to the temperature at which it melts. So that's going to be the mass of the ice, the specific heat of ice, and then the change in temperature of the ice, keeping in mind this is just going from the initial temperature, which is going to be negative 40, all the way up to 0 degrees. At 0 degrees, the ice is going to melt, and it's going to undergo the latent heat of fusion that I talked about. And then it's going to take some energy for the ice, which is now water, and that's going to undergo a temperature change from 0 degrees all the way up to 20 degrees here. So we can look up what all these guys are. I know that the mass of the ice is 0.2 kilograms. I know that the specific heat of ice is going to be 2100 joules per kilogram degree Celsius. The change in temperature going from negative 40 to 0 is going to be a positive 40 change in temperature. Again, the mass of the ice is 0.2 kilograms, and the latent heat of fusion is going to be 3.34 times 10 to the 5th joules per kilogram, very big number. And then lastly, I'm going to have the mass of the ice, 0.2, and now it's melted water, so I'm going to use the specific heat of water, 4190, put my 1 in there, and then the temperature change now is going to be 20 degrees Celsius, going from 0 degrees to 20 degrees. All those are going to add up, and I'm going to get 1.004 times 10 to the 5th joules. Now I go back up and I use this expression right here. I'll change my color to green, and I'm going to say that the negative 251,400 times the mass of the water must be equal to this 1.004 times 10 to the 5th, and I can solve this for the, I'll put a negative in there, the negatives are going to cancel out, and I solve for the mass of the water to be 0.399 kilograms. Okay, take a second to read the problem. I have a rod that is made out of copper, and it has a hot side and a cold side. I know the hot side's at 100 degrees Celsius and the cold side is at 0 degrees Celsius. And I also know the surface area is going to be 1.25 centimeters squared. That's going to be 1.25 times 10 to the negative 4th square meters. I always want to work in meters. I also know that the length of the rod is 45 centimeters long, so 0.45 meters. I'm asked to find the final steady state temperature gradient along the rod. That is going to be quite simpler. The temperature gradient is going to be the hot temperature, temperature hot, minus the cold temperature, temperature cold, divided by the length, and that's going to be my temperature gradient. I'll just say temperature gradient. Simply, that's going to be 100 minus 0 divided by 0.45. I go ahead and I punch those guys in, and that's going to tell me that my temperature gradient is going to be 222 degrees Celsius per meter, and that's also Kelvin, degrees Kelvin per meter. So that's my temperature gradient, part A. Now for part B, I'm asked to find what is the heat current in the rod in that final steady state. So that's going to be the thermal conductivity of copper multiplied by the area, multiplied now by this temperature gradient, temperature hot minus temperature cold, divided by the length. So the thermal conductivity of copper is going to be 385 watts per meter squared degree Kelvin. I know that the surface area of the rod is going to be 1.25 times 10 to the minus 4th meters, and I've calculated out my temperature gradient already, so I don't have to recalculate it. 222 degrees Celsius or degrees Kelvin per cubic meter. So my heat flow is going to be 10.7 watts, and that is also going to be how many joules per second is flowing over the rod. Okay, so for this problem we're going to take a second to read it. Here we're going to have a tungsten sphere, and that sphere is going to be emitting radiation. Remember, all things are going to emit radiation simply because they have a temperature. I know that the emissivity of tungsten is going to be 0.350, so it's not a very good emitter, it's not a very good absorber. I know that the radius of the sphere is going to be 1.5 centimeters, or 0.015 meters. I know that the temperature of the sphere is going to be 290, so temperature of the sphere is going to be 290 Kelvin. And I want to maintain this this sphere at a constant temperature of 3000 Kelvin. So essentially I need to add heat into the sphere to keep the temperature the same. It's losing heat in the form of radiation. I need to keep on adding heat to that. I also know that the heat can be related to the surface area of the sphere multiplied by its emissivity, multiplied by the Stefan-Boltzmann constant, multiplied by the temperature to the 4th minus the temperature that it is emitting to the 4th. So lastly, I know that the area of a sphere is going to be 4 pi r squared. So the heat I must add into this sphere is going to be 4 pi multiplied by the radius squared, 0.015 squared. The emissivity of the tungsten, 0.35. The Stefan-Boltzmann constant, 5.67 times 10 to the negative 8th. And now I'm going to here have my temperature I'm trying to maintain, 3000 to the 4th. Subtract off the temperature that it's losing through radiation, so 290 to the 4th. And I go ahead and I calculate that out, and I'm going to calculate 4.54 times 10 to the 3rd watts. That's how much heat, how many joules per second I need to add to the sphere in order to maintain that temperature of 2000.